Okay, we're going to pick up where we left off in the last video. In the last video, we made our first computer programs, and we used 4 different programming languages. I'm on my desktop here in my Linux command line. I type ls-al. That lists out all of the contents of this directory, right? So we created, first we created Python. We can look and see what that looks like. Cat helloworld.py. Right? And then we created one for Bash, the .sh extension. Okay, it's slightly different. And then we created one for JavaScript. This is Hello World. And then we created one in C. Now in C there was a source code file, which was just a plain text file. All right, and you see it's quite a bit more complicated. And then when we try to cat the compiled version of this program, we compiled it and turned it to a binary file that the system can understand and execute. All right, system level instructions are stored in this file, and it's just binary data, just like a text file. All right, but a text file has a specific format, and we're going to talk about what that means. All right, now when I try to cat hello world, we get gibberish. It's because not all of the characters, not all of the numbers in this file, the binary numbers, correspond to Ascii characters. Right? And so when the terminal doesn't know what to print out, it tends to print out different types of junk. Right? Okay, so we are going to discuss a little bit about binary to get familiar with the Ascii numbering system. All right, so Ascii, we've pulled up this document before. This is an Ascii chart, Ascii table. All right, and all of the characters common on the keyboard you'll see appear here, but there are also some characters that can actually be represented in binary, but they don't make sense to write in a text editor. Okay, for example, the tab character, that's actually just one character, but every text editor or Word document or anything knows that when you press tab, there's actually you're supposed to display, by default, it's 8 spaces. All right, in this text editor, it translates tab into 4 spaces for me. It does that automatically, and that's just the text editor. Okay. Normally, when you would hit the tab character, it is just one character, even though text editors will represent it as 8 spaces. It's only one actual Ascii character that's stored in the file numerically as binary data. All right. We also learned about the line feed. Line feed is a new line character. Right. We can't really represent that in the text editor, because when we create a new line character, the text editor is supposed to just go to the next line like that. Okay, but there is technically, when we store this data in a file, there's technically an Ascii character that represents a new line character. All right, and there's lots of these different characters that most of the time we don't use in our everyday lives, but all of these over here, this basically covers every single thing that you can press on the keyboard. All right, and there's a numeric value associated with each one of these. Okay, so this Ascii table ends at 127 in decimal. Up here we've got decimal, hexadecimal, octal. All right, so the Ascii table ends in 127, and it starts at 0. So if you add 0 to that, that means there's 128 decimal values for every single character represented on the Ascii table. Okay, now that has significance in terms of number systems. All right. So let me paste this over here, this little chart. Okay, so here we have 4 bits of information. Okay, what is a bit? A bit it stands for binary digit. Okay. So the last 2 letters here, IT, and then the first letter here, B, BIT, bit, is a binary digit. So that means a 1 or a 0. So a binary digit is just a 1 or a 0. This is also commonly referred to as a Boolean flag or a Boolean value. Now we'll get to what Boolean means here in a little bit. So depending on how many digits we have in binary, that's how many bits we're talking about. Okay, so what are all the possible numbers you can write with one binary digit? Well, you can only use all of the digits in the alphabet of that particular base one time. So the alphabet in base 2, you can use a 0 or you can use a 1. And it's important to remember that these are just symbols. We could use a circle and a square or any number of things, but the point is that there's only 2 of them. Okay? Once you run out in the Arabic style numbering system, you have to add another digit to the left. Okay? So here, in this ones place, how many possible digits can we have? Or how many possible numbers can we have with one digit? Okay? One place, one bit. You can have a 0 or a 1, so there's 2 possibilities here. Alright, we have one digit, so that is 1 bit, 2 possibilities. There we go. Alright, now what about 2 bits? 2 bits. Okay, what can we have? Well, we can have, with 1 bit we can have a 1 or a 0, and that's 2 possible outcomes. With 2 bits we can have 0, 0, 0, 1, 1, 0, and 1, 1, and that equals 4 possibilities. Okay. What about with 3 bits? Three bits we can have 0, 0, 0, 0, 0, 1, 0, 0, or 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And if we count all these up, we've got 1, 2, 3, 4, 5, 6, 7, 8. There's 8 possible numbers that we can write with 3 bits, 3 binary digits. Okay? So it turns out that this is because we take the base of the number system we're using, which in this case is binary, so the base is 2. Base raised to the number of digits. If we have 1 digit, then 2 to the first power is just 2, which is our number of possibilities. Okay? Here we have 2 digits, 2 binary digits. So we take our base, this is binary, so it's base 2, and we raise it to the number of digits. So 2 to the second power. 2 squared is 4, so we have 4 possibilities. Okay? Over here we have 3 bits, and we have 8 possibilities. That's 2, which is our base, raised to the number of digits, the number of places. We have 3 digits. Okay, this is a 3-bit number. So 2 to the third is 8 possibilities. And let's just do one more. We've got 4 bits. Okay, so this one's going to be a bit longer. This is going to be 2 to the 4th. Okay, so what are the possibilities for 4 bits? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, or 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and we have 8 so far, right? And if you look here, this is basically the same numbers that we have for our 3-digit numbers. Okay, if you look at the last 3 digits here, 0, 0, 1, last 3 digits, 0, 0, 1, 0, 1, 0, last 3 digits, all the way up. See, 0, 1, 1, we have 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, now the only difference, the remaining possibilities here are the same set of numbers except without a 0 in front. We have a 1 in front. Okay, so up here, instead of a 0 in front, we have a 1. Okay, so you see now we have 2 to the 4th possibilities. Right? 2 to the 4th is 2 times 2 times 2 times 2. Right? So 2 times 2 is 4, squared is 16, so there's 16 of these. And you see each time we add a digit, we're doubling the number of possible numbers that we can create. Alright, the first time we could create 2. If we double that, we add a digit, we can create 4. Okay? Basically, if you add a digit in front, you can either have a number with a 0 in front and then the rest of the digits, or 1 in front and then the rest of the digits. So each time it makes sense that we're just doubling it. Right? So the next one, 3 digits, it's all of these 2-digit numbers. Right? 0, 0, 0, 1, 1, 0, 1, 1. It's all of these numbers except with a 0 in front, and then it's all of those numbers with a 1 in front. Okay, so there's 8 possibilities. And the same thing happened with when we moved from 3 digits to 16 digits. Okay, it's the same series of numbers as the last set, except you can either have a 0 in front or you can have a 1 in front, which means that there's going to be double the amount of numbers from the last number of digits. Okay, so basically, depending on what your base is, you always multiply the base when you add a place, when you add a placeholder. Okay, so for example, if this was if this was base 10, we have 9 possibilities here, and then if you add 0, it's 10. So there's 10 possible numbers we can write with 1 digit. Now we don't double it. If we have 2 digits, we don't have 20 possibilities. We have to multiply by our base. So we know intuitively, because we've been around the Arabic decimal number system our whole lives, we know that if we have 2-digit number or 2-digit decimal number, what are the most what are all the different numbers that we can create? How many can we possibly create with 2 digits of decimal number data? Okay, 2 digits of decimal number data goes from 0 to 99, right? So 1 through 99, that's 99 numbers, and if you count 0, that means there's 100 numbers. So 2 digits of base 10. So that is 10, our base, to the 2nd power. Right? How many numbers can you write with 3 decimal digits? Well, each digit there's 10 possibilities for, so it's 10 times 10 times 10, which is 10 to the 3rd. So with 3 digits of decimal data, 10 times 10 times 10 is 1,000, and we know that to be true. We have 3 digits of decimal data, and we can write up to 999, right? That's obviously 999 numbers, different numbers that we can write, and if you count 0, then that's 1,000. Alright, so this is important to understanding binary and the relationship between binary and hexadecimal and decimal. Okay, so we have 4 bits there. So how does this tie into Ascii in the Ascii character set? Alright, so we keep looking at this chart. This chart is a way to represent character data numerically, because we know everything that gets stored in a computer is binary data. That's what gets stored on the hard drive. Binary data is what's stored in RAM, and binary data is what the input and output is of the processor. The entire system runs on binary data. So we have to have ways of translating from decimal data or character data or any kind of data. We have to be able to translate it to binary. Alright? So let's look at the Ascii character C. This is a lowercase c character. Okay, so let's examine this a little bit. So we have the Ascii character C. If we look on our chart, the Ascii character C is 99 in decimal, and it's 63 in hexadecimal. Okay. Now this just happens to be the binary representation of that. Okay, how do we know that? Alright, well, let's look at the place values. Okay, this is the units place, so this is the zeros place, or the ones place. We have 2 to the 0 power. That's a 1. 2 to the 1st power, this is the 2's place. 2 to the 2nd power, that's the 4's place. right? And as we go up, under here, I'm pasting, this is the digit place. In decimal, we're used to this being zeros place, tens place, 100s place, 1000s place, 10,000s place, right, etc. In binary, it's really the same thing, except you're going up by the power of the base, right? So base 2, so you multiply by the base each time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 10, or 16 times 2 is 32, 32 times 2 is 64, and etc. We get to 128. All right. So let's see what this binary number actually turns out to be. Okay. So we have a 0 in this position. This is the 128th place. So it's 0 times 128, and then we add to that the value of this place. We have a 1 in the 64th place, so that's 1 times 64. We have a 1 in the 32nd place, that's 1 times 32. We have a 0 in the 16th place, 0 times 16. We have a 0 in the 8th place, so that's 0 times 8. 0 in the 4's place, 0 times 4. A 1 in the 2's place, that's a 1 times 2. And then a single unit left over. We have 1 in the 1's place, so that's just 1 times 1. All right, and if we go ahead and make that a little bit easier to read, we have 0 times anything is 0, 1 times whatever you multiply by is the same value, so this is 64, 32, 0, 0, 0, and then we have 1 times 2, which is a 2, and then a 1. When we add all these up, the final value is 64 plus 32, and 66 plus 30 is 96, plus 2 is 98, plus 1, right? So that's 99 in decimal, and that is equal to our ASCII lowercase c. All right? So we see that this number here, this binary number, they're still the same number, they're just different ways to represent that concept. Again, remember, numbers are abstract concepts, and there's lots of different ways to represent them. So we're just picking a system and going with it. A lot of things in computer science are like that. Though there are various other character representations than ASCII. Okay, one of the most common today is UTF-8. That is used on the internet, and it's used practically everywhere. All right, but there are many different types of character encodings. And it's basically just a system of communication. We're agreeing on what these numbers mean. When I open a file and I see a whole bunch of numbers in it, the file consists really of just ones and zeros. But I'm deciding that every block of characters that I see, or block of numbers, I'm going to treat that as if it was a character in this chart. Okay? So remember, bit is a binary digit. Now up here, byte is the next big unit in binary, and a byte is 8 bits. Okay, so it's a block of 8 bits. So here we have 1 bit, 2 bit, 3 bit, 4 bit, 5, 6, 7, and 8. Okay, so this is an 8-bit number. This is also known as 1 byte. Okay. Now our ASCII chart goes from 0 to 127, which that is 128 different possibilities. Okay. So we see 2 to the 7th is 128, but this is the 128th place. Okay. If we put a 1 here, this number would already be, if we just had the binary number 1 0 0 0 0 0 0 0, right? That's 8 bits. That's already greater than our ASCII table. We have a 1 in the 128th place, which already makes the number bigger than anything in our chart. Okay, so our chart, the ASCII characters themselves, are only 7 bits. It takes us all the way up to 7 bits. All right, so 2 to the 8th is 256, and that's how many 8-bit binary numbers you can write. So remember, it's the base to the power. So over here, 1-bit number, it's the base to the power. Okay, so if we have an 8-bit number, then that is the base to the 8th power. Alright, and that equals 256 possible numbers. Alright, if we back up one and we go 7 bits, we would just divide by our base. So 256 divided by 2 is 128. And we do that again if we want to go back down to 6 bits. It's 2 to the 6th. Okay, what's half of 128? 64. We'll go 5 bits. What's half of 64? 32. Okay, what's half of 32? 16 possibilities, 4 bits. Okay, so when you want to know how many different numbers you can write given a certain number of digits, right, you always take the base of the number system you're working in and you raise it to the power of the number of digits. Okay, so this means in a byte here, a byte is 8 digits, 8 binary digits. In a byte, we're only using these for ASCII characters. Okay, 2 to the 7th power, there's 128 possibilities in the ASCII table. Alright, so we only use these digits when we write something in ASCII. Alright, and so there's an extended ASCII table that uses that last digit. Okay, now this adds some extra characters. Alright, some of the stranger characters, greater than equals, that sort of stuff like that. You don't see these all too often, but they do exist and the computer can render them. Okay, so this really isn't used that much anymore because, like I said, we've moved on to other character encodings like UTF-8. However, UTF-8 is backwards compatible with the original ASCII table. So UTF-8 looks at every byte of information. Now remember, a byte of information is 8 bits. And if there's a 0 in the front, then it knows the next 7 bits are regular ASCII data. Okay? So whenever there's a 0, it knows the next 7 bits is just the regular ASCII code. If there's a 1 here, then it knows it's a different set of characters, right? So when computers were originally developed, there wasn't much space, right? We have tons of hard drive space and RAM now, computer memory. We did not have, space was very much conserved back when computers originated. Okay, so every bit really mattered. And so they didn't have all of the character encodings for all of the languages. Right? Now, if you think about all the different languages that exist in the world, especially Asian character sets, right? They're vastly different. So you need a binary representation for every single one of those characters, right? And we see that pretty clearly that 1 byte of information isn't going to satisfy that, right? So UTF-8 actually uses 4 bytes of information. It can use up to 4 bytes. All right? If it sees a 0 in a byte, then that character representation is only 1 byte. So if the very first digit here is a 0, UTF-8 says, okay, this is just an ASCII character and I'm only going to look at the next 7 bits, and that's the character that it is. If there's a 1 in this byte, then it knows it's in a larger set of characters and it's going to read the next 2 or 3 or 4 bytes of information to figure out what that character is supposed to be. Alright, now that gets a little bit more complicated, but it lets you understand a little bit about how computers are all about systems and organizing data and translating data to numbers. That's why it's important. You have to have a system, otherwise it's just a bunch of zeros and ones. Okay, ASCII is a standard. It's a standard for understanding character data as binary numbers. Alright, so let's look at a little bit more about this ASCII C character. Alright, so this is a lowercase c. So in ASCII, this is obviously the lowercase c. In decimal, this is 99. in hexadecimal, this is 63, and in binary, this is 01100011. Okay. Now, really, the binary number stored on the disk, there's no space there. Generally, I add the space here when we're just talking about numbers, just kind of like how when we write a decimal number, we have comma separators to help us see visually how many space, what set of characters we're on. Right. So normally in binary, you'll break it up into 4 chunks and put a little space in between. Okay. But on the disk, it's actually stored together, just like that. Alright, so that's binary data. So let's examine this. We've got binary number 0110 space 0011. Okay, we'll put a little separator here so we can look at this section. Okay. So this binary number is basically all this information that we just did right here. Alright, I'm going to paste this down here. This is binary. That's our binary representation. I'm going to delete it from up here. So again, all of this we're talking about the ASCII character C and the different ways you can represent that. Alright, I'll put that down there too. So the ASCII C character. So this is how we can prove that this binary valuation of the ASCII character C does equal 99. Alright, now let's look at the hexadecimal version. Okay, if we look at our ASCII table, we see lowercase c, right, there's our decimal 99, and we see 63. So in hexadecimal, this is 63. Alright, so we've got our 2 digits of hexadecimal data. Alright, now this is not unlike the binary representation, except we're using a different base. Hexadecimal is base 16. Okay, so we have this digit is our base to the 0 power, just like over here in binary. It's our base to the 0 power. So this is the units digit, just like over here in binary. The difference is we can have 16 different digits to work with. Alright, when we move on to the next digit, this is 16 to the first power. Just like in binary, it's 2 to the first power. And in decimal, it's 10 to the first power, because this is the tens place in decimal, right? So when we look at these powers, this is 16 to the 0 power, this is the ones place. 16 to the first power is the 16s place. Alright, now let's combine the place values with the actual digit value that's stored there. Okay, so we have a 6 in this place value, and this is the 16's place value. So this is 6 times 16 plus 3 times 1. Alright, 6 times 16 is 96, and then 3 times 1 is just 3. And again, we get the same output, 99 in decimal. And that is equivalent, based on this chart, the ASCII lowercase c. Okay, so now we want to talk about the relationship. We're starting to see a pattern and a relationship between binary and hexadecimal and decimal. There's a special relationship between binary and hexadecimal, though, that is very important, and that's why you see hexadecimal show up so much in computer science. All right, and we're going to talk about that relationship now. Okay, so we have 1 digit of hexadecimal base 16 numbers, right? There's the base times the number of digits, and it's 1 digit number, so there's going to be 16 possible arrangements. If we look at a 4-digit binary number, that's base 2. Okay, so there are the base times the number of digits. There's 4 digits, So that's 2 to the 4th. That's 2 times 2 times 2 times 2, which is 16. So we see 1 digit of hexadecimal is equivalent to 4 digits of binary data. They're interchangeable. So whenever I see a hexadecimal digit, I could just slap in a 4-digit binary number, and those two things are equivalent. All right, and I've made a little chart here to illustrate that. Okay, so this little table here, we have decimal here. We're all familiar with this. It goes up to 10, 11, 12, 13, 14, 15, right? There's 15 numbers, and if you count 0, that's 16. Same with binary. So binary, we know the representations of binary. That's 0, 0, 0, 0, 0, 0, 0, 1, and as we go down through here, you see patterns emerging. We have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. All the way down this column, they alternate 0, 1. Down this column, they alternate 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. All right? So computer science, a big part of it is pattern recognition. This is important to understand permutations and all the different possible arrangements of numbers. Okay? In this column, what do we see? Do we see a pattern? We've got 4 zeros and then 4 ones. I mislabeled this here. This is there. We've got 4 zeros and 4 ones, and then 4 zeros and then 4 ones. Okay? Now in this column, we double the number of zeros. We had 4 zeros and then 4 ones. Now we have 8 zeros and 8 ones. And if we add a digit, then we'll have 16 zeros and 16 ones. Okay, so there is a pattern here. But you see, here we are at 0, and up here we're at 15. And you see we've completely run out of digits in binary. The only way to make a bigger number in binary here is we have to add another digit to the left. Okay, so for 4-digit binary numbers, this is as big as it can get. Alright, now in hexadecimal, we have base 16, so there are 16 individual digits. Right, so we go 0 through 9. So 1 through 9 is 9, and if you add 0, that's 10. Right? And then we have 6 more of these characters. Right? So 10 plus 6 is 16. So we have a total of 16 characters. Right? So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay? So again, you see 15. There's obviously 15 of those, and if you count 0, then that's 16. Now what this means is any one of these hexadecimal numbers, A, that is represented, that is the number 10 in decimal, but it can be represented in 4 binary digits. Any single hexadecimal digit can be represented in 4 binary digits. That relationship is why you'll see hexadecimal data on computers all the time. Computers speak binary, and hexadecimal is a more concise version of binary. Okay? It would take a whole lot of space to write out everything in binary, and it's also kind of hard to read. We get a better sense of reading hexadecimal numbers because we can tell if they're big. If you have a 2-digit hexadecimal digit number and it starts out with an F, you know that's going to be a fairly large number, right? So F6 or something like that, or B, BA, right? B, we have a better sense of what that means, right? So there's an 11 in the 16s place. So right away that's going to be 11 times 16. And then A is 10, so there's a 10 in this place, and that's the ones place. So it's 11 times 16, and then plus 10 times 1. Alright, so this chart's very important. Okay, so let's go back to our hexadecimal number 63. And then we also have our binary version of that. Okay. So remember, we're looking at the Ascii character C. That's 99 in base 10. And in binary, that is 0110 and then 0011 in base 2. Right? That's binary. 63 is this is hexadecimal, base 16. Okay, so if we look at the digits, hex is 6, and then the second digit is a 3. In binary, the 4 digits are 0110, and then the next 4 digits are 0011. Now remember, we already proved that this is equal to 99 in decimal and this is equal to 99 in decimal. So there's a very interesting relationship that emerges. Look at this chart. We have a 6 here in hexadecimal. That's equivalent to 0110. And what do we have here? 0110. All right, and we have a 3 here. What's that in a 4-digit binary number? A 3 in hexadecimal, well, 1-digit hexadecimal number is equal to 011. All right, 0011 in a 4-digit binary version of that number representation, right? 0011. So we see at any point it's very easy to convert to hexadecimal from binary or vice versa. Okay, so in hex, all I do is I look up the number in a chart. I can make this chart real quick, and I look up the number 6, and there's the binary representation. Slap it in there. All right, I look up the number 3. There's the binary representation. Right, I slap it in there, and that can work both ways, though. Now the only tricky thing is with binary numbers. If I wanted to convert the number, let's just write some random binary numbers here, 110101 1110. Okay. Now this is tricky because I can't just take these 4 digits. All right. Everything in our number system starts on the right-hand side and moves left. Okay. So I have to start with the rightmost number of bits. Okay, so let's do this underneath. Back to this example, we just see that 6 is base 16, and that is the same as this base 2. 3 is base 16, and that's the same as this base 2. So this is just showing what you look up in the chart, right? So here's a different example. This is example going from binary to hexadecimal. Okay, so here's a binary number. We can do the same thing, but we always have to start on the right hand side, okay? Because we can add zeros to the left of a number, right? In decimal, if I have the number 1, that's the same as the number 01. That's the same as the number 001. Okay? 002. 003, right? If there's a 0 in this place, it doesn't matter. So we can have an infinite number of zeros on the left hand side. But I can't just add zeros to the right. That changes the value completely. This is now 10, this is 20, this is 30. Okay? So we can only add zeros to the left. Alright? And what we want to do is we want to add zeros until we have chunks of 4. Chunks of 4-bit numbers. And then we can just pop in a hexadecimal value for it. Okay? So we started with this number, and we added zeros until we had chunks of 4, and now we just look up in our chart 0011, so we are in the zeros. 0011 is 3, so this is going to be a 3, and then we have 0101. Okay, so 0101 is a 5, and then we look at 1110. So 1110 is an E. Okay, so this binary number is equal to 35E in hexadecimal. What does that equal in decimal? Okay, well, we have a 3 in the 16 to the 2nd powers place. And then we're going to add a 5 in the 16's place. So that's 15 to the 1st, or 16 to the 1st power. And then we have an E, which an E is 14. So we have 14 of these units. So times 16 to the 0 power. So again, it's the same thing. The base to the 0 power, and then what is the number in that position, right? So we have an E. We have to translate that to 14 real quick. 14 times 1. 16 to the 0 power is 1. Right? 16 times 16 is 256. And that makes sense when you think about it, because 2 digits of hexadecimal data, There's 16 possibilities here and 16 possibilities there. 16 times 16 is 256. Right? So this is the 256th place plus 5 times 16 plus 14 times 1. Right? So 256 plus 256 is 512. 512 plus 6 is 518. Plus 50 is 568. And then 768. So 768 plus 5 times 16 is 80. And then 14. We add these up, and we have 768 plus 80 is 848, and then plus 14, 852, 862. Okay. So we can get out a calculator and double check my math on that. Maybe. Alright. So 3 times 256 plus 5 times 16 plus 14. 862. Okay, so that's the relationship between binary and hexadecimal, and it's very important. It comes up all the time in computer science. Right? And that's also a nice relationship when we look at the hex dump of, let's look at the sh file. Okay, this is just the cat command, but if we look at the hex dump -c, we see we're looking for a lowercase c. Okay, so here's one, and this should be the hexadecimal value 63. Alright, so we've got 1 character, 2 characters, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the 13th number here should be 63. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and sure enough, right here, that is the character C. Now it's an 8-bit number, even though ASCII character set only takes 7 bits. Okay, so in this character encoding, when I look at a file, it looks at 1 byte at a time. So 8-bit chunks, and it looks for an ASCII number inside of each one of those bytes. Okay, so that's why we can look at this number with Hex Dump. We can look at this as 23, because it's just 2 4-bit numbers. 4 plus 4 is 8. It's an 8-bit chunk. These 2 hexadecimal digits are a byte. Okay, so up here, when we were talking about a byte equals 8 bits equals 2 hex bits. Okay, so 1 byte equals 8 bits, and it also equals 2 hex bits. Okay, so that should be enough for this video, and I am going to continue with one more with dealing with these files that we were talking about, and then we'll be done.